All right, everybody, welcome back to more data analysis. I'm Robert Bassett. We're going to be talking about today simple linear regression in matrix format. So we just come out of a lecture which is simple linear regression. Today we're going to add this important caveat in matrix format. And so let's get started. So chapter 11 in Truth About Linear Regression is where we're getting started. You notice that we're bouncing around a little bit in Truth About Linear Regression. We're going to introduce some notation that comes later in the textbook, a little bit earlier in this class. All right, so first things first, we're going to recall some facts about linear algebra. Okay, so for matrices A and B, double transpose, so this T here denotes a transpose. If you take the transpose of a matrix twice, you get the original matrix back. So remember with the transpose operator, what the transpose operator is, it takes a matrix and basically if you have a bunch of rows, it turns all those rows by taking the transpose operator and puts them into columns. So transpose swaps the role of rows and columns. Okay, so this sort of makes sense. You swap rows and columns, you swap again, you get back to the original. But these are just facts we're going to have to remember. The other fact about transposes that I want to remind you is that if you multiply two matrices A and B, and then you take their transpose, to get the result of that, you can first apply B transpose multiplied by A transpose. So this is sort of confusing, but what happens is AB transpose is B transpose A transpose. So you switch the order and you apply the transpose to each of them. Okay, so this is just a fact about transposes, which you'll have to remember. This actual same property about transposes holds for invertible A and B. So if A and B are invertible, A times B, the matrix A times B, the inverse of that matrix is B inverse times A inverse. Okay, so it works exactly as transposes does. You swap the order, take the inverses. And so another fact. And then the other thing I want to mention is, this is just notational. If you have two column vectors, A and B, so by a column vector, what I mean is this is a matrix which is n by 1. Right, so it has n observation or n rows, one column, so it's just a column. Okay, so if I write A transpose B, what I'm doing is I'm taking the matrix multiplication of A transpose. When I take the transpose, I swap row and column, so I get something that looks like this, right? Times something that looks like this, which is a column vector, right? And if I take the matrix multiplication of this, I do rows times columns. This is just a scalar. Okay, and in fact, A transpose B for column vectors A and column vector B, this is their inner product. So you may have denoted inner product of A and B as like AB or something like this in your calculus classes, your vector calculus classes, or your linear algebra classes. But we're going to use this A transpose B, and we're generally going to assume, unless otherwise noted, that that vectors are column vectors. Okay. All right, so linear algebra facts coming at you hard and fast. I will mention, please check on the course website on Sakai if for the resources I've posted there, the Matrix Cookbook, which has a nice collection of linear algebra facts, and in fact all the linear algebra facts we're going to be using in this course in case you feel like you need to knock off the rust on your linear algebra skills. All right, so recall the simple linear regression model. So this is from before. This is from the previous lecture. We assume the simple linear regression model is that y is a linear function of x, right? So there's a slope, or there's an intercept, there's a slope, and there's an epsilon term. We have some various assumptions, which we have those three assumptions that we talked about last time. The mean, zero, constant variance, Gaussian noise assumptions on epsilon. And so what we're going to introduce in this lecture is matrix notation, which is going to make the bookkeeping easier on our estimates of these beta 0 and beta hats. Okay, so this whole lecture is basically going to be notational. Okay, so it's going to be what we've done in the previous lecture, but in this matrix notation. And the reason that we're going to do this is that it's going to allow us to extend to new settings very easily once we have this nice matrix notation. Okay, but there's going to be a little bit of a learning curve if you're used to working with scalars and not matrices. So if we have a sample of endpoints, okay, and our sample comes in form of x and y pairs, okay, we're going to construct the following matrices. A y matrix, which is actually just a column vector, okay, of the y's, okay. So this is n rows by one column. And we're going to have an x matrix, which is a ones vector, and then the x, right? So this is n by 2. And beta, which is column vector of the beta terms, which is 2. Okay. So this matrix X is going to be very important to us. It's called the design matrix. Okay. So I have this column of ones here. This is important to remember. Now I'm going to ask, what is X times beta? Okay. So if I multiply X times beta, what do I get? So X beta, so I'm going to do row by column. So X beta, if I'm going to do row by column here, I'm going to get 1 times beta 0 plus x1 times beta 1. I'm going to get beta 0 times 1 plus x1 times beta 1. And then for the second row, I'm going to get the dot product of this row and this column. I'm going to get beta 0 plus x2 beta 1, and so on. Okay. So what I get when I do x times beta for this matrix, for this design matrix X, what I get is actually this part for evaluated at different x's. Okay, so this is important because this is a concise way of writing the linear this line here. Okay, for evaluated at different x's. So notice the role here of the ones vector. So what the ones vector is doing when we do this matrix multiplication is, because this is a 1, it gives us the intercept term. Okay. Okay, so x beta, so we've just expanded this out. I did this on the previous slide, but just writing it out more pretty here on my slides. And so y minus x beta, okay, y minus x beta, this is again that vector y from the previous slide. I have a vector of y's minus x beta, do y minus this term here, I get this. So this is actually, you'll notice, let me back up just a bit. So this is actually, this is y minus, minus this expression here, right? So this should be just a bunch of epsilons, right? So y minus the x part, okay? So y minus x beta transpose times y minus x beta, what is this? This is actually, well, you can think about this. This is the vector, which is, we're taking the inner product of a vector with itself, okay? Or the dot product, another way to say that. And what happens if you take the inner product of a vector with itself, you can sort of write this out. You get, right, this matrix multiplication, this element times this element, plus this element times this element, so on and so forth. But when we take that transpose, what you end up getting is the sum of squares. Okay? When you take the inner product of a vector with itself, you get this sum of squares. Okay? So this is important because it allows us to write some of the things that we've been talking about in previous lectures here more concisely. So we'll notice this is sort of reminiscent of something we might see in a mean squared error term. And so we'll expand that a little bit. So if we define beta hat as a vector, which has beta hat 0 and beta 1 hat, okay, we can define the residual vector. So the residual vector E, this is just a, as its name suggests, it's a vector of the residuals, is the truth minus the predicted. Okay, so from the previous slide, we defined the residual EI is yi minus beta 0 minus beta 1 at xi. Right? So when I write this, I have y minus, and here, since I'm using the predicted betas, I get this expression here. So here I have a vector of all these residuals, okay, a column vector. So the mean squared error, we've talked about the mean squared error is the mean of the sum of the square residuals. So we'll just break that down a little bit. So if we have a residual, we have these residual vectors, we can take the inner product of it with itself. This is equal to, right, this is just expanding out the definition of the residual vector here. And this is obviously, let me just be especially clear here, but this is 1 over n times a summation of the residual square, right? And we saw from before in the previous lecture that the sum of the square residuals, we take the mean of them, that is the mean squared error. Okay, so we have mean squared error is this expression, and then actually these are all just this is just an inner product. We can just do some matrix algebra here to expand out this thing. Okay, so what are we going to do? So transpose. I did not mention this on the previous slide in terms of facts about transpose, but you might remember this from your linear algebra class, that if you take the transpose of a sum, you can distribute that across the sum. Okay. I say that because we're going to distribute a transpose across both of these terms. So I'm going to distribute the transpose, and I'm going to go ahead and expand. Okay, so if I distribute the transpose, I get a y transpose. I apply the transpose to this term. What happens? Well, remember from the linear algebra facts on earlier slides, we switch the order and we apply the transpose to each of them, right? And so we'll do that. So we get a y transpose y, that is this term transpose times this term. Okay. We get a y transpose x beta, that's this term, y the transpose times this term. We get a beta transpose x transpose y, that is the transpose applied to this term. So we flip their order and apply transpose to each of them, and then gets the y. And then there is beta transpose x beta, which is apply the transpose, flip the order, times this term. So another fact we have about transposes is that if you have a scalar and you swap rows and columns, it does not change it. It's just a scalar, right? Scalar is you can think about as a 1 by 1. You swap rows and columns 1 by 1, it still stays the same. So if A is a scalar, transpose has no effect. And then we can actually break this down. Beta transpose x transpose y is a scalar. Okay. So what that means, according to this property, is that it's equal to its own transpose. Okay. So why is this thing as a scalar? Why is this thing a scalar? Let's break it down, right? So remember, beta hat, just going to make some notes on the side here. Beta hat is a column vector. It is 2 by 1, right? There's beta 0, beta 1 by column. X, remember, was this design matrix. It was n by 2, n rows, 2 columns. Y was n by 1. So what I want to show is that this thing is 1 by 1. So let's just quickly see about the sizes here. So beta transpose, because rows and columns swap, it's 1 by 2. X transpose is 2 by 1. And y, or excuse me, 2 by 1. X is, the x1 becomes 2 by n. And then y is n by 1, right? So when we matrix multiply these, what happens? You remember what happens to shapes when you matrix multiply. This becomes a 1 by n, right? Times n by 1, which becomes a 1 by 1. Okay. So that shows that this thing is a scalar. So since it's a scalar, it's equal to its own transpose. Okay. What happens when we apply the transpose to this? Well, we apply it to each one and we flip their order. So we say, so this becomes y transpose x double transpose, which is just x, beta double transpose, which is just beta. Okay. So that's this expression here. And so what this tells us is that this term is equal to this term, because this is the transpose of this, or vice versa. Okay. So that allows us to collect this individual piece here we have this 1 over n y transpose y minus twice this expression plus this expression here. And this twice here comes from the fact that, as I just said, we showed that this expression is equal to this expression because it's a scalar and they're transposed of one another. All right, so linear algebra hard and fast. Let's keep moving. So we reduced the mean squared error to this expression. And so what we're going to do next is we're going to re-derive the least squares estimator. That is the least squares estimator is that those betas which minimize the mean squared error. We're going to re-derive it in matrix notation. Okay, so we're going to let b, instead of having a dummy variable, have dummy variables b0 and b1 as we did in the simple linear regression lecture. We're going to let b be a dummy vector this time. And so the mean squared error for the estimate b, as we discussed in the previous slide, we had this estimate beta hat, and reduce it down to this expression. And so if I plug in this dummy variable b, the mean squared error for that estimate is this expression. Okay. And so to minimize this mean squared error, we're going to take a gradient with respect to b and set it equal to 0. And to do so, we're going to rely on a little bit of matrix calculus. Okay, so we'll talk about about some of those rules coming up next. But the idea is basically the same as in the simple linear regression case, right? In the simple linear regression case, in the previous lecture, we were just working with scalars. We took this partial derivatives, we set them equal to 0 and solved. Here we're going to take a gradient with respect to b, set it equal to 0 and solve. And so same idea, but just in matrix notation. And as I mentioned, this is going to help us when we're expanding, in particular when we're working with multiple predictors. Matrix notation is going to be much easier. Okay, so a little bit of matrix calculus review. So if f is a scalar valued function of some p-dimensional input vector x, okay, so x is p-dimensional, f is scalar valued, then the gradient is the vector of partial derivatives. Okay, so the gradient of f is the vector of partials. And we're for our convention, some people use different conventions, but our convention we have vectors as column vectors unless we specify otherwise. So it's this is a vector and it's a column vector by default. Okay? Because there's p partial derivatives in there for the p-dimensional vector of x, it is p by 1. So we denote the Hessian. So the Hessian, which is we have a second derivative there, suggestive. It's like a second gradient, is a matrix of second partial derivatives. Okay, so I hope you have seen this in your calculus classes what a Hessian is, but quick reminder that it is so we'll denote it by this double nabla is this expression here, f. And what it means is that the ij element of this Hessian matrix is the second derivative of f. You take one derivative with respect to xi, you take one derivative with respect to xj. Okay, so and it's symmetric because you can take the second derivative of xj equals xi. There's some facts from calculus lurking in there, but what it means is that this element of the matrix, you've taken one derivative with respect to xi, one derivative with respect to xj. Okay. Some people denote the Hessian operator instead of a nabla squared here. They do a nabla transpose. There's some reasons that makes sense, but we're going to use this convention. So if you see this in some textbooks, it means the Hessian. All right, and so what's some properties of this gradient vector and the Hessian matrix? So if A and B are scalars, and bold A and bold B are matrices of compatible dimensions, what that means is that compatible, what I mean is that matrix multiplication is allowed, right? So their shapes permit matrix multiplying. It's not incompatible dimensions. And we have f and g as functions which maps some p-dimensional vector to some scalar. Okay, so there's scalar output, p-dimensional input. Then the gradient operator satisfies some properties. The first one is linearity. So this is just like the derivative, that you can distribute the derivative across the sum and pull out constants. Okay, so that's what we've done here. Distribute the gradient across the sum. This is a sum of two functions. Another property here is what happens when we take the gradient of a matrix multiply. Okay, so here we're taking the gradient with respect to x. Just be very clear here that we're taking the gradient with respect to x, and we multiply this x vector times some matrix A. Well, what happens is, this is similar to actually the scalar derivative. When you take the derivative of constant times variable, you just drop the variable and you're left with constant, right? So this is just a slight extension for gradients instead of the scalar derivative, but it extends as we might expect it. Except there's a twist, right? And the twist is that matrix multiplication is not commutative. What that means is that x transpose A is not equal to A transpose X is not equal to A X transpose in general. Right? And so we have to actually keep track of matrix multiplication the other way. Right? So what happens if instead of multiplying the x out front, we multiply the x out back of some matrix B? Well, what happens then is that the result is the matrix where we have to transpose the B. Right? So B tags along, x drops, but in order to account for the fact that we're working with a matrix setting instead of a scalar setting, we have to transpose the B. Okay? So if x is out back, you have to transpose. If it's out front, you just get to keep the matrix. All right. The last fact on this slide is quadratic forms. Okay. So a quadratic form is something that looks like this. So you have a variable x. Okay. And you have a p by p matrix. So remember, x is a p-dimensional vector, it's a column vector, and c is a matrix which is p by p. So this is a quadratic form in x. Okay. And in general, its gradient is given as follows. So you take the gradient of a quadratic form, it's the following. So it is c plus c transpose times x. Okay. Again, let's think about how this extends from the scalar case. So let's say these were scalars. These were scalars. We would have, this is a scalar, this is a scalar, this is a scalar. We would have x squared times c, right? Because we could just rearrange these because scalar multiplication is commutative. So we could rearrange these, get x squared times c, and then x squared times c, if we took the derivative of it, we get 2 times c times x, right? That's just the scalar derivative. Well, how would that look here if these were scalars, right? We would have the gradient of x squared times c. We would get c plus c transpose, but since c is a scalar, if we were working in the scalar case, we would get 2cx, right? So this actually generalizes the scalar setting. So it works when c and x are scalars because c equals c transpose, so we get 2cx here. All right, so these are just some matrix facts. All right, so more things about matrix facts. So we say that a point x star is a stationary point of the function f. It's also called a critical point if the gradient of f evaluated at x star is 0. So that vector of partial derivatives is 0. And I should say here, when I write 0 here, I mean the 0 vector. Okay, so it is a vector of zeros. So let x star be a stationary point. So that is, it's a point where the vector of partial derivatives is 0. Okay, so here's some facts. If the eigenvalues, okay, eigenvalues, scary words you've heard from linear algebra, they're going to come up in this course, but for now, we're just going to remember that this is something that comes out of a matrix, these eigenvalues. The eigenvalues, here's the fact, of this Hessian matrix are positive. Then this matrix is said to be positive definite, and this stationary point is a local minimum. Okay. So what this is telling us is this is basically extending the second derivative test from calculus. So in the second derivative test, what we can do is we have a stationary point. We can take the second derivative. If it's positive, then it tells us that we have a local minimum. And in the multi-valued setting, in the where we have x as a column vector instead of just a scalar, we have to look at the eigenvalues of the Hessian matrix instead of just looking at the sign of the second derivative. Okay, so if the eigenvalues are positive, then the Hessian is positive definite, and the x star is a local minimum. If the eigenvalues are negative, then this Hessian matrix is said to be negative definite, and the point is the local maximum. Okay, so this is just extending the second derivative test again. And I'm positive that you have seen something like this in your vector calculus class, but this is coming at you fast, so you may have to look at that. Look at it again to remind yourself, but we won't use this fact too deeply, but just to remind us that, hey, eigenvalues are the things with which we can test local minimum and local maximum. If the eigenvalues have mixed signs, so some are negative and some are positive, then the stationary point is said to be a saddle point. Saddle point so called because it looks like a saddle. In some directions it's a minimum, in some directions it's a maximum. And just a slight extension, but if some of the eigenvalues are 0 and the rest are positive, then you would say this Hessian is positive semi-definite. And similar for negative. If some of them are 0, you say semi-definite instead of definite. And the conclusions above still hold, but the local maximizers and minimizers might not be strict. Okay, so what that means is, for example, you might have something like this, right? Where this point here is, yeah, sure, it's a local minimum, right? But it's not a strict local minimum because we don't have this bowl shaped. And this sort of thing happens when you have a eigenvalue of your Hessian matrix, which is 0. Okay. And so I summarize this in the slide as maybe flat. So this is sort of some flatness instead of being bowl shaped. So this is an example of as a strict local minimizer, where points near are strictly larger than the value at x star. All right. Okay, so let's go back to minimizing our mean squared error. We have introduced some facts about matrix calculus. Hopefully, reminded some facts about matrix calculus. So we're going to rederive again the least squares estimator, this beta 0 and beta 1 hat, in matrix notation. So we previously showed that the mean squared error is equal to this, where we combine this term because that one term we were looking at was a scalar, therefore it was equal to its transpose. And so we want to minimize it. So we are going to take the gradient using our new fancy matrix calculus rules and set it equal to 0. When we do that, what's going to happen? So we're going to minimize in this b vector. Well, there's no b in this. This thing's going to be 0. This is a linear term. This is a matrix times b. So we have the rules for dealing with matrices times b. And this thing here is actually a quadratic form. Okay? The reason it's a quadratic form, we have a variable on the outside with some matrix x transpose x on the inside. Okay? And I think I should be clear here. I was sort of using x as a variable when I was talking about the matrix calculus, but here when we're talking about data and least squares estimator and these kind of things, we're talking about x as the design matrix that I talked about, which is n rows and 2 columns, where you have the ones vector and the x input, okay, and y is that column vector. And so we're switching a little bit from x being our variable when we're talking about the matrix calculus stuff generally, whereas here b is our variable of interest. Okay, so just keep your head about it there. So taking gradients, set n equals 0. As we talked about, this thing goes away. We're left with this piece here, which the b term is out back. Remember, when b is out back, what happens with the gradients? Well, we take the transpose of what's out front. We take the transpose of what's out front, because we're taking the transpose of a matrix product, we switch their order. Okay. And then we're left with the quadratic form here. What happens with the quadratic form? Well, remember from the slide just a moment ago, what we do is we do x transpose x plus x transpose x transpose all times b. Okay. And again, just as in the scalar case, this is a critical moment where we switch from a general b to, once we set equal to 0, this defines our least squares estimator, or the beta hat, which has minimum mean squared error. Okay. Perfect. So what is x transpose x transpose, right? So we have this piece here. That's a lot of transposes. Let's go ahead and simplify it. Remember, we apply the transpose, we switch their order, apply them to each of them. We're going to get x transpose, that's the one here, switched order, apply the transpose, times x double transpose, and x double transpose is equal to itself, so x transpose x. So what we've just shown is that x transpose x transpose is equal to x transpose x, okay? So these quantities are the same, okay? In other words, this is any matrix, this is just a fact here, but any matrix which is equal to its own transpose is called symmetric. Okay. What that is we sort of swapped rows and columns and it didn't make a difference. So this x transpose x matrix, because we've shown that when we take the transpose, we get it back, x transpose x is symmetric. Okay? So this allows us to combine this thing here. We get twice x transpose x beta hat. Okay? I can pull out the 2 from both of them now because we combine and get a 2, and so I left with 2 over n, this piece here, and then I get, again, this x transpose x piece. Okay. I can divide out the 2 over n, 2 is not 0, n is not 0. This gives me that this term is equal to this term, just by moving this x transpose y on the other side of the equation. All right. Perfect. So we're moving right along. We have we've done some simplification here. Now, how do we solve for beta hat? Well, assuming that x transpose x is invertible, right? And again, at this slide here, we can apply x transpose x inverse to both sides, cancel out the x transpose x on this side, and be left with beta hat is x transpose x inverse x transpose y. All right. So this does assume that x transpose x is invertible. We're going to get to this point later. In general, it's kind of difficult for x transpose x to not be invertible. So we're going to just assume it is for now, and we will talk about it in the future, sort of a more advanced topic, and we're going to open up a big Pandora's box there. But so if x transpose x is invertible, this is our solution for beta hat. And also, we've talked about some eigenvalue conditions. I just sort of wanted to throw some eigenvalue language out there because we'll see it again. The eigenvalue condition that we reviewed, the sort of second derivative equivalent, which shows that this beta hat is a minimizer instead of a maximizer. It is true, so this Hessian matrix of this function is positive definite. If you take a little bit, you can show it, but we're not going to go through the details. All right, so in our univariate derivation, it took actually quite a bit of bookkeeping, right? We had to keep track of all these different equations, and here these solutions are actually equivalent, right? So it's the same minimizer, obviously. We've just done one in one notation and one in the other. But the matrix version, this is a solution for a vector, right? So this is solving for a vector. So we have both beta 0 and beta 1 hat in this one expression. We don't have to keep track of these two equations for beta 0 and beta 1 hat. Okay, so in that sense, the matrix version is equivalent, assuming you can keep track of your matrix rules and your how to take gradients of matrices. That makes the matrix version better because you just have to remember this one expression and it gives you both beta 0 and beta 1 hat. Okay? Okay, so we have just shown that beta hat, the so-called least squares estimator, that's that estimator which minimizes the mean squared error. So it gives the least squares, the least sum of squares, the least mean squares error, mean squared error. We've shown that it's this expression. And so how can we write the predicted values y hat in terms of this new value, this estimated value beta hat? Okay, so remember y hat, we showed earlier in this lecture, we showed that y hat is equal to x beta hat, right? So, well, here that is. But we can actually expand out beta hat using this, what we derived here, and just plug in what we know. So that's just plugging in beta hat here. So what this is kind of interesting, actually. So this is the predicted y, is we apply this matrix to y. So we take y, we apply whatever this matrix is, x times x transpose x inverse times x transpose, we apply it to y, we get y hat. So this is a special matrix which will have some special properties. It's called the hat matrix, okay, and we'll denote it by this h. So y hat equals hy. Okay. Now, it's called the hat matrix. Why is it called the hat matrix? Well, this is punchline, but it puts the hat on y, right? So this thing is h. If you apply h to y, you get y hat. So it puts the hat on the y vector. I hope that's clear. So this is actually its name in statistics. I always get a chuckle out of it because it's sort of a great name for it. Okay, so the hat matrix satisfies some important properties. First, it's symmetric. Okay, what that means is that it's equal to its own transpose, as we discussed earlier. It is idempotent. Okay, idempotent. It's either Latin or Greek. I forget exactly, but idem means same, and potent means power. Okay, so idempotent means same power, and what it is you take h, you square it, you get h. It's the same as taking power, take square, right? So idempotent, h is idempotent. Also, h it gives us some properties of influence, okay, and this is going to be also important to us in future lectures. But what this means is that if you take the partial derivative of your predicted y for the ith observation with respect to your input j, your input y at the jth observation, that is hyj. Okay? This is sort of hard to parse when you look at it first, but what it means is basically this. What do I mean by influence here? What I mean is that this is sort of an important thing, but sort of how much do our predictions change with respect to our inputs, right? So let's say you can imagine a situation where we didn't get exactly the same y's, we got some slightly different y's. Okay, let's say we changed this yj just infinitesimally. We made it a little bit larger, a little bit smaller. What would happen to our prediction in that case? Does our prediction change dramatically if we just change this y a little bit? Intuitively, we think that's bad, right? That's just like you change my observation just a tiny bit, infinitesimally so, the rate of change of this predictor, or this prediction, with respect to this input, y, this received value, observation y, is this hij, right? So if the hij is very large, it suggests that very small changes in y give us very large changes in magnitude in y hat. Okay, and that's important because it tells us sort of how much each input y influences each predicted y. Okay, so this is what we mean by influence. We have the rate of change of the predictions with respect to the input. All right, just some linear algebra chat. A matrix which satisfies properties 1 and 2 is called an orthogonal projection that is symmetric and idempotent. Okay, we will investigate what that means. We say it's an orthogonal projection. Think about projecting onto something. Projecting onto what, right? We'll talk about that in future lectures, but while we're introducing the hat matrix, we'll mention that it has these properties. Before I move on to this example, let's just actually think about why this is the case, right? How could we show this? Symmetry, it actually relies on one important property, which I haven't mentioned, but you can convince yourself that it's true, and that is that the inverse of a symmetric matrix is itself symmetric. Okay, so this is sort of if it exists. Okay, so not all symmetric matrices are invertible, but if it is invertible and it's a symmetric matrix, its inverse is symmetric. The reason that will matter is that in order to show that H transpose H equals H, you can look at this, you can apply the transpose, you're going to have to swap their order, take the inverse of this inverse matrix, but actually what you can show is that if this inverse is symmetric, that is, you apply the transpose to it, it equals itself, then this whole matrix H will be symmetric. Right? You can imagine, you pull this, switch the order, put this out front, put a double transpose, becomes X, put this out back, put a transpose, it becomes X transpose, you get H back. Okay. Oops. Similarly, if you square H, okay, if you square H, what happens is you get an X transpose X. You're going to put this thing times itself again. You get X transpose times X. One of them cancels with the inverse, and you get H back. Okay, so just some properties there. I'm getting a little sloppy with my pen here. All right. So let's do an example in R. So the example I want to do in R is the div USA. It's sort of sad, but this is divorces in USA data from the Fairway package. This package is sort of suggested by the name that you're going to use it to investigate divorces. I think it's sort of interesting because we have a column which gives the number of folks in the military per 1,000 population, and it can relate to other things like marriage rate, birth rate, different things. So it keeps track of these statistics over the years, and I think it's an interesting data set. So we're going to perform this regression. So we're going to regress this Y folks in the military per 1,000 population onto how many marriages there are per 1,000 population. We're going to verify that this least squares error this least squares estimator, matches from LM. So we're going to compute it using matrix notation, verify that it matches what's done in LM. Okay. So we need to know that a couple of things. We need to know that this sort of awkward chain of symbols gives matrix multiplication in R. We need to know that the T function gives a transpose of a matrix. We need to know that solve applied to a matrix will compute its inverse. Okay. We can use rep to build a vector of ones. So if you do rep 1, n. It will generate a vector of n, ones. And then we can actually stack vectors together using matrix or using cbind. Those are both ways to stack vectors together. Okay, so this is the example we're going to do. Let's switch over to R next and take a look. So here I have the fairway package. I will mention that some people I find, especially those on Macs, sometimes fairway package will not install due to some Fortran issues linking your RStudio install with Fortran. Needless to say, if you have issues accessing this package, send me an email and I will get this div.usa data for you in another format so you can follow along. But I'm going to load it up and just pull up the help menu really quick. So we'll just double check. So as I said, this data set is looking at divorces in the USA, so keeping track of them from the years 1920 to 1960. But again, as I said, my interest is primarily not in the divorce rate, but instead keeping track of marriages, military personnel per 1,000 population as years go on. Okay, so we'll just do some initial data exploration here. So I'm just going to plot year as the x-axis, military per 1,000 population on the y-axis. Here we see what we might expect here. So year going along the x-axis, we see this large bump from World War II. And what happens to marriages? So marriages are a little more all over the place, but this is actually marriages as a function of marriages per 1,000 people as a function of military per 1,000 people. Let's see. We see maybe some positive trend here. Right? These cluster of points seem to be moving up together. There's sort of some. This is pretty noisy, but I might suggest that there is a small positive trend there. I didn't plot this one, but just because I'm curious about it now, I want to see what does the marriage rate do. How does the marriage rate change as a function of years? So let's put that one in, and it's here. It's marriages per 1,000. And here's what we see. So we see a big decrease in the 30s, increase in World War II years, and sort of steady decrease with some peak in the 70s, it looks like. Interesting. I'm no social scientist. I don't know what's going on there, but interesting to see the numbers. All right, so let's actually compute this least squares estimator. Again, so this is we're trying to stick a line through these points. Okay. So what I'm going to do is I'm going to build my design matrix. Okay, so let me just pull this up here so I have it. But remember, the design matrix X is these pieces. So I'm going to build this design matrix X, which is a column of 1s and a column of X's, and I'm going to build this Y vector Y. So the way that I'm going to do this is I'm going to use cbind. So cbind glues vectors together into a matrix. I'm going to give it a 1s vector, which is I'm repeating a 1 times the number of rows in the data times. And then the second column is going to be that X column. So this gives me my X, the design matrix, and my Y vector is just the vector military. Right? Remember, I'm predicting number of folks in the military with marriages. I'll go ahead and define that. And then beta hat, as we saw in the lecture, so beta hat is supposed to be scrolling down, so you can see what I'm putting in here. Come on. So beta hat is X transpose X inverse. times X transpose Y. Okay? So what I'm doing here on the left is exactly that. So X transpose X, so this is X transpose X, and then I'm doing solve. As I mentioned in the slides, solve will take the inverse. So this is X transpose X inverse times X transpose Y. Okay? This will give me my beta hat, print it, this is what I get, and I can put the least squares line on the plot. So indeed, it looks like we have this positive trend here because this is the intercept and this is the slope. The slope is positive. Okay? And so, yeah, you notice beta hat comes out as a matrix here, which is interesting. So to query, to get beta 0 or beta 1, we have to get the first element here and the second element here, like this. Okay. So does this match R's LM? Well, let's see. LM gives me the coefficient. So I've done military regressed onto marriage. Data is div USA. And let's just see. So we have negative 8.95, 8 something something, right? So subject to rounding here at this decimal, we see that yes, indeed, we do match. This is just because LM will print will only print so many digits, right? So subject to rounding, yes, they agree. And so we know that we've checked LM. We see that we've derived what the least squares estimator is, and then we've showed that LM seems to be doing that. So yes, indeed, behind the scenes, R's LM is solving this. How you actually compute this X transpose X inverse is actually sometimes computing the inverse can be computationally burdensome, and so R is going to do something a little more clever under the hood to not compute that inverse entirely, just to compute this matrix multiplication without having to compute the inverse first. But we won't worry too much about that. This is indeed giving us the right answer. Okay, so let's jump back into the lecture. Let's see where we are here. Okay, so instead of jumping back into the lecture, I have a pause here. So we've been lecturing for a little bit. I'm going to take a pause, and then I'm going to come back and do, for the second part of this lecture, probability with random vectors instead of probability with random variables. And so we're going to see some results in a little bit of different direction, so it's a good time to take a pause.